So we discussed the Oqpsk, and we see now that Oqpsk is a modified version of QPSK, and in this case, we say that one of them, in particular the Q channel or the code reset channel, is shifted in phase by delaying the bit stream in that channel by half of the bit interval. So you don't delete the full bit interval, but you delete by a half of the bit interval. So by that, what that achieves is that the transitions do not happen at the same time. This is just the diagram that we worked with earlier for the QPSK, but I have brought it here so that I can demonstrate where we adjust the transitions. So as you can see, we have the odd bit sequence and we have the even bit sequence. So in the QPSK, the transitions can happen at the same time. But with the Oqpsk, you delay the quadrature channel. Here is a correction. The 1/2 of the bit interval is incorrect. Actually, this is 1 bit interval. The 1/2 bit interval will happen for the pi/4 shifted QPSK. I have just observed that error, and therefore I believe we will see that the delay is not by 1/2, but rather it's by 1 bit interval. Because as you can see, 1 symbol of QPSK takes 1 symbol, it takes over 2 TB. Therefore, when you delay 1 bit by 1 TB, it will happen at this point. So I'm clearing this, and I'm saying that the quadrature will be delayed by 1 TB. So it will happen at this point. And for that reason, we will see that the transitions will never happen at the same time. There is a disadvantage of QPSK, which is the transitions happening at the same time. The total phase shift is equivalent to 90 degrees plus 90 degrees, that is 180 degrees phase shift. That's a very huge transition, but with the Oqpsk, we limit the magnitude of phase shift to maximum of 90 degrees because we are saying that the one of the Q channel is delayed by 1 TB. So as we have seen, mathematically, the Q is delayed by 1 TB, and as you can see, what we'll see is that now the transitions are going to be happening twice the number of times that happens at QPSK. Reading on, we see that the stages in the I channel occur at the midpoints of the Q channel bits and vice versa. So as you can see, this is the I channel, and this transition is happening midway through the simple period of the I channel. There is never more than a 1 single bit change in the die bit code. So what we see is that the transition that is happening here can only represent only 1 bit code. So you can only move from 10 to 11 and never moving from 10 to 01. They cannot change at the same time. So for that reason, what you see is that we will only be having a transition that is maximum of 90 degrees phase shift. And therefore, that is what that statement means. So we say now that the Oqpsk ensures that I and Q signals have transitions at the time instance separated by TB, and therefore this is incorrect. I believe that we have seen the transitions are separated by 1 TB and not TB/2. So this is a block diagram of the Oqpsk. As we have seen in QPSK, the binary data stream is arriving at the rate of FB bits per second, and the bits are encoded using bipolar non-return to zero encoding scheme. And after they are encoded, therefore they are given the pulses of positive and negative going pulses. They are separated into the odd and even bits. And just like we did with the QPSK, the odd bit joins the I channel, and the I channel is multiplied by the balanced modulator with the cosine carrier signal, and we have the I or in phase channel added with the Q phase or quadrature channel. And what you see before we get to this point is that the quadrature component or bit stream is delayed by 1 TB by this block diagram, and the delay allows us to see, just like we have seen in this in earlier on, that the bit stream are going to be 1 bit period behind those of I channel. After the delay, the 90 degrees phase shifted carrier signal is multiplied by now that bit binary encoded, bipolar encoded non-return to zero bit stream to form the Q signal or the quadrature component of the Oqpsk. So these are summed up, and therefore at this point we are able to get the Oqpsk signal. So in summary, the operation of Oqpsk may be summarized as follows: that the bit stream is applied to a bipolar non-return zero encoder for line encoding, and then we say that the odd bits are separated from the even bits, and the quadrature data sequence starts with a delay of 1 bit period after the first odd bit is available. So we can see that delay allows us to reduce the maximum phase shift that the Oqpsk signal will have. And therefore, this delay is the one that gives the name O offset to QPSK. Therefore, it becomes called Oqpsk, and the in-phase sequence is applied to the in-phase path balance modulator, the quadrature data sequence, and is multiplied with the 90 degrees phase shifted version of the carrier signal to form the Q path or the quadrature component of the Oqpsk, and the outputs are summed together to form the Oqpsk. What we observe is that each bit in the I phase or Q bit sequence is held for a period of 2 TB seconds, and that every symbol contains 2 bits, which are, and therefore the symbol period is equivalent to bit duration.